up the two descriptions of the line we worked with in the last video. This describes that line as a single vector equation. This describes the same line using parametric equations, so it's a triple of equations. And of course, these formulas for x, y, and z just become the component functions for the single vector function r of t. I want to just show you there's a third way that we can describe this, which is called the symmetric equations. What I'm going to do is work here with these parametric equations. Each one of them has a t in it because I'm describing x, y, and z in terms of this parameter t. And so I can solve for t in each of them. But if I'm describing a single point on the line, it's the same t value that gives me the x value, y value, and z value that go with that one point. Obviously, if I change t, I'm now talking about a different point. So what I'm going to do is I'm going to solve for t in each one of these things. So I can say x minus 1 is 2t, which would mean t is x minus 1 over 2. Looking at the equation for y, I could say y minus 2 is negative 6t, which means t is y minus 2 over negative 6. Okay. And solving for t here, I could say z over 2 is equal to t. But again, it's got to be the same t that's giving me a triple of x, y, and z that go together. So if I simply say, hey, t is equal to t is equal to t, well, then I get x minus 1 over 2 is equal to y minus 2 over negative 6 is equal to z over 2. And that right there is my symmetric equations. So that's basically where you solve for the parameter in each of the parametric equations. Now, that's not going to work if t doesn't show up in every single component. If you had something like z was just 2, so that we were constantly at 2, I wouldn't be able to solve for t here. So I wouldn't be able to find symmetric equations for that particular line. Symmetric equations are going to work when your direction vector has non-zero components in every one of the components. Okay. But when it does, you can work with something like this. And you'll notice I can pick out from here what my starting point and what my direction vector are. The numbers that I'm subtracting from x, y, and z give me the coordinates of my starting point. 1, 2, and 0. There's my starting point. The denominators, 2, negative 6, 2, give me the components of my direction vector. I will just caution you, do be careful. This is the standard form for the symmetric equations that I have. Notice I've got one copy of x minus a number, one copy of y minus a number, and one copy of z. If I wanted to, y minus 2 over negative 6, it sometimes looks a little bit weird to have a negative on the bottom. We don't often do that. So I could bump that negative to the top and say that's negative y minus 2 over positive 6, which would become 2 minus y over 6. Totally fine. That's equal to z over 2 and x minus 1 over 2, but this is no longer in standard form because it's not just one copy of y. So do be careful. Don't just say, oh, this number occurs in this set of equations, so therefore it must be the coordinate of a point. Double check that you've got things in standard form before you start picking things out. In fact, let's just try an example. Let's suppose I have a line defined by x minus 3 over 4 equals 5 minus y over 2 equals 1 minus z over 3. Okay. Tempting to say that my direction vector will be 4, 2, 3, but I notice that the only one of these that's in standard form is the x one, because I've got one copy of x. I would want to rewrite this. I can factor out the negative 1, so I can say that's negative y minus 5 over 2, but then I'd want to rewrite that as y minus 5 over negative 2. Okay. Same thing here. I can factor out a negative 1, so it's negative z minus 1 over 3, which I would then write as z minus 1 over negative 3. So once I get the symmetric equations into standard form, now I've got x minus 3 over 4 equals y minus 5 over negative 2 equals z minus 1 over negative 3. Now I can pick out the coordinates of my starting point and the components of my direction vector. So now if I wanted to get a vector equation for this line, I could say r of t is my starting point would have as its coordinates the numbers I'm subtracting from x, y, and z, plus t times my direction vector now is going to be these numbers in the denominator. But notice I did have to manipulate to get it into standard form before I could just pick out those numbers.